Hello everyone. This is the second session of this week. I will keep continuing our discussion about the machine learning overview. Machine learning can be further categorized according to the problem we want to solve. If we want to find function when both y and x are given, that is a supervised learning problem. In this case, people try to find function f that minimize the MSE in the data. Most of the prediction and inference problems are supervised learning. The name of supervised comes because finding this function f is supervised by observed data y. When y is unknown or hidden, and only x is given, if we want to find out f in this setting, it is unsupervised learning. Because there is no y to guide f, it is unsupervised. In this problem, we find f that describes relation among x, input value of x. Clustering is a typical unsupervised learning problem. For example, data points with x1 and x2 are distributed in this way. How many groups actually you can see? The clustering is grouping samples with the different cluster. There are the different clustering. This is one case of clustering. This is another case of clustering. Which one looks better? Definitely, this clustering looks better for the most of the people. Definitely, there are good and bad ways to cluster the data. Finding good way, which means the finding good function f. This is the clustering problem. Here, keep in mind that there is no given or true y. We just want to find f within the x. The result of x can be the assigned cluster. Semi-supervised learning is something between supervised and unsupervised. For example, supervised clustering or prediction after dimension reductions. In this course, we will not actually seriously cover this semi-supervised learning. Another major branch of the machine learning is reinforcement learning. In a reinforcement learning setting, a machine usually gets a reward according to its actions. The goal of this learning is to find the next action that maximizes the rewards in the current situation. Here, reward is often coined as y, and the action and environment they are given as actually as an argument of this function f. However, the training set of the x and y. So do we need in order to know f, we need the x and y. However, initially the training set of x and y are not given. A machine experiences these rewards by some trial and errors. It's the difference between supervised and reinforcement learning. Throughout this course, we will mainly discuss about supervised, unsupervised, and reinforcement learning. Here, let's a little bit discuss more about the prediction problems. A typical supervised learning problem. After some discussion, we will reach the final conclusion of the bias and variance trade-off. Even though I will explain the bias and variance trade-off with the prediction problem, it's a general concept that can be applied to the unsupervised and the reinforcement learning. Anyway, let's focus on the prediction problem at this moment. Given a data set, we want to estimate f that makes actually small mean square error, not in the given data set, but in other data sets. The other data set, usually we haven't observed them. This is a key point. For example, we want to build a predictor of a heart attack with a blood pressure using the data collected from 2001 to 2005. However, we want to test this predictor's performance using the data collected from 2006 to 2010. Totally independent data. This is why the performance of a predictor should be tested in an independent dataset. Again, a predictor is built in a given dataset, which is called training set. Then it should be tested on the independent dataset. The performance should be tested in the independent dataset, which is called as a test set. This is the basic the prediction problem settings. Please keep in mind that all these the observed samples are random samples from an imaginary whole population. Our goal is finding out this fx of this whole population only using the random samples of the training sets. So if we really have a good estimation of this f hat that wrapper this true f, then this f hat should work well for another random sample of the test sets. Here, so we can say there are two types of the mean square error, two types of the MSE. MSE in the training set and MSE in a test set. When we estimate f using a training set, we can actually reduce MSE in a training set as much as we can. So as much as we want by using more flexible or more complicated models. Let's consider a problem to classify. Let's consider this case, a problem that classifies with the light and dark blue points. Okay, in the two-dimensional space of x1 and x2, these two groups of the data points are located like this. So in order to find out some decision boundary that classify these two groups of the samples, what gonna be the good decision boundary? Intuitively, you may want to use this black line to separate two groups of samples. This black line is now it becomes the red line. This line is quite smooth and separate this dark and light blue points reasonably well. Of course, there are some misclassified point like this. However, you can consider they are actually from the noise or reasonable errors. So this is one possible choice. How about if you want to use much simpler decision boundary like this linear boundary. Okay? This is simple and it's not flexible. So because it is too much simple, it doesn't fit the data well. We can say because there is a lot of the misclassified point. Okay? In this case, we say this the non-flexible model underfit the data. Okay? In contrast, we can use more complicated and flexible model, like this cyan line. This curve is actually very wiggly, but it can perfectly classify these two groups of the data point. But do you think it's a good classifier? Intuitively, You don't think so. You don't think so intuitively. This is not good because it actually fits too much to this data, for this given data. That means it is not expected to be good as well for new random data. So new kind of another data set. So in this case, we say this model actually overfit the data. So bottom line is, if a model is not flexible enough, it underfits the data, and it has the large MSE in the given data. So okay, so the given data, that means in the training data, and also it has the large MSE in the test data set, another data set. Okay, so this graph actually shows, this figure actually shows, this x-axis is a flexibility, and y-axis is the MSE, and this curve is for the training MSE, and this curve is for the test MSE. Okay, so if a model has the very low flexibility, it has both high MSE in both of the test and training there, because it underfit it. But by we increase the flexibility, we can actually reduce MSE in both of the training and test set. However, after certain point, the test MSE start to increase as the flexibility, while the training MSE keeps down. For a model with very high flexibility, like this wiggly line, this model has a very small training error, but it has a very large test MSE because it overfit it. The relation between MSE and the flexibility is generally coined by bias-variance trade-off. The MSE, after some calculation, the MSE, the y minus f hat square, expectation of the y minus f hat square, it can be rewritten as the variance of the f hat plus bias of f hat square plus variance of the error. So this two part is a reducible error, and this is an irreducible error. This reducible error can be separated into the variance part and the bias part. Variance part and the bias part. So reducible error is the sum of the variance and the bias. Let's see what are these the bias and variance actually means. Variance of the f hat is how much f can vary when trained by different training set. Ideally, since the f hat refers the true f, because f hat refers the true f, so ideally f hat should not vary that much. However, as a model getting more flexible, it is easy to be trained differently by different data set. So it has the high variance. Bias is actually the refers error introduced by approaching a real-life problem. A model f hat is always different from f. Then how much it is different? Since the actual world is complicated, simple and non-flexible models are easy to have the high bias. That means the large variance, large difference to the actual truth or to the real world data. Then in this case, we say it has the high bias. Okay. We can illustrate this point with such figures. If a model has the low bias and the low variance, so let's consider center point is true F. Center point is true F. If a model has the low variance and low bias, whenever it is trained by different data set, the resulted estimation of the model gonna locate around these centers with a small variance. This means low bias and low variance. However, it has the high variance with low bias. Their center, they still centered at the true F. However, because they have a very high variance, they gonna train differently by different data. So they are distributed widely, in a wide range. That is a high variance. How about it has low variance and high bias? Okay, so in this case, because they have a high bias, they are actually far from the true fx, but they actually locate very closely to each other because they have a low variance. Then how about the high bias and high variance? You can easily see it gonna look like this. So the point is that there is a trade-off between bias and variance. If we increase the model flexibility, the bias gonna decrease generally, but variance gonna increase. If we decrease the model flexibility, variance gonna decrease, but bias gonna increase. So we have to sacrifice one to have the other. There is no free lunch. It's why we have the U shape of the curve for the total errors. Finding the minimum point of the total error around this point by adjusting this the flexibility, this is actually the art of the machine learning. Okay, so let's see this point with a the simple example. Here we will use the simple KNN method, K nearest neighbor method. KNN is a totally non-parametric supervised learning method. It determines the class of a sample according to its the nearby sample point. For example, there are the two groups of samples. One is dark blue, the other is in the light blue. Then, for example, if we want to determine the class at this the x point, then if we use the KNN method, the predicted class at this point is depends on its neighbors. For example, if we use the k equal to 3, that means we gonna only refer 3 nearest neighbors. That will be this one and this one and this one. Among these 3, because we have this light blues are 2 and dark blue is 1, so in this case we determine this x point as a light blue. However, if we use the k equal 5, that means we look at the 5 nearest neighbors. Then among the 5, we have 3 dark, 2 light. So we determine this x point as dark blue class. It is very simple. However, because it's non-parametric, it's also powerful. So it's like this. In KNN, the flexibility is actually controlled by this k. If we use the low k, small k, it follows every single point, so it has the high flexibility. When k is equal to 1, like this, the black line, the decision boundary is like a black line, so it actually captures all of the the single data point. It is like a black line. However, when k is high, it actually considers the many data point, and one model gonna be similar with the others. So with the large K, it has the low flexibility. When K is 75, we're gonna have a decision boundary like this, the blue line. It is almost like the linear line. Okay. So by changing this K, we can actually measure, calculate MSE in both training. This is for the training, and this is for the test. Okay, test set. According to the K, actually the x-axis is the 1 over K. So when K is 1, which is this side, it has the high flexibility. And when K is low, when 100, it's 1 over K is the 0.01, so it has the low flexibility. So flexibility increase in this way. Okay? So by increasing or adjusting the value of the K, we can see this the training error is keep going down, but this test error shows something like the U shape of curve. So this is the typical stuff, typical example of the bias and variance trade-off. Okay, so even though I explained this the bias variance trade-off with the prediction problems, it is a general concept that can be applied to the unsupervised or reinforcement learning. Anyway, so throughout this course has 3 parts. The first part is about supervised learning. The second is for the unsupervised and the reinforcement learning. And the third part is about deep learning. In these days, deep learning is so popular. So deep learning is kind of the collection of the models for the function f, especially based on the the neural nets. So since in these days the deep learning is so popular, so we prepare a separate session for this deep learning. Okay, so here is the summary of this week. Machine learning is to find specific rules from the data, which is mathematically defined by the y equal to the fx. And the prediction problem is to guess y when y is given, and the inference is to select the important x for y. Generally, low model flexibility means the high interpretability, high bias, and low variance. And high flexibility means low interpretability and low bias and high variance. And there is the trade-off between the bias and variance trade-off according to the flexibility. You're gonna see about this the bias and variance trade-off throughout all of this course. Okay, so here are some references you may want to refer. Okay, so I'm gonna finish up here. Okay, so thank you very much.